All right, guys, so we're going to work with an idea or a concept called continuity. And the word itself kind of is self explanatory. And the idea of continuity, it has to do with the word, it's right here in front of me, continuous. So, an idea of a continuous function is if I have a function like a line like this, and I take my pencil, let's say, I'm just going to use a highlighter instead so you guys can see it. And if I can take my pencil along this line and I can go like this and continuously keep going, then it's said to have continuity. Okay? So that's the idea. But if I change it, let's say, go back to drawing, and let's say I draw something else. Say I draw this, and I draw that, and then I have a line over here like this, and it's a linear line. And this piece is on my graph. If I've got to take my pencil and follow it along, all of a sudden now I jump, and there's a break in the line, so therefore it's not continuous anymore. So that's the idea between continuous and not continuous. So the next level of that, and there's three or four types of continuity, and we'll talk about them in class. But to prove a function is continuous at x equals c, in other words, like if I had this function here and it went like this, and I had another line that went like this, and this was at x equals 2 right here, like this is at x equals 2, then the idea is this: is this function here continuous at x equals 2? That's what it's really saying. So now you have to have 3 steps. You must include 3 steps. All 3 steps have to be written to get credit if you're proving continuity. So let's tackle this here real quick. Let's look at some examples. So this is my first question here. You know what? And I'm going to make it a little bit larger. Let's see if that works. There we go. This is my first question here. So I've got this function. We're just working with 1 right here, and it says this. It says, is f of x continuous at x equals 2? So let's just draw this graph real quick here. Where's my shapes? There we are. Let's just draw a quick graph. I'm going to draw a quick graph right here. Okay? And it is x plus 1. So I'm going to go up to, oops, I need to go to my equation. No, drawing. And I go up to 1, and it's a slope, and it kind of goes like that. That's what my line looks like. So if I really look at it and I use my highlighter, I'm going to go, oh, looky there. It's continuous because my pen doesn't jump anywhere along this line. So let's prove that using one that we know is continuous. So we have to take the idea of, oops, I shouldn't have done that. We have to take the idea first, does the function exist at c in general? In other words, can I put in an x and get out a y? So this means, can I put in an x to get out a y? That's what f of c means. So they did that here. So how'd they do this? They took f of 2 and they said f of 2 exists because f of 2 is equal to 2 plus 1. So f of 2 is equal to 3. So my first point is taken. F of 2, when I plug in 2, I get an actual number out, which is 3. That means it exists. So then we go to the next one. Does the limit of the function exist as x approaches c. Well, c here is 2. So if I go over here to this one, and it's 2, I want to know, does this limit exist right here? Does it exist right there? Why did it not do green? I want a green. Why does it exist right here? Well, you look at it and go, yeah, it does. It approaches that. But remember, you have to prove these things algebraically. So we're going to go, okay, well, the limit of x as x approaches to of f of x, which is the limit as x approaches to of x plus 1, what's our first rule? We plug this in. I plug it in, gives me 2 plus 1. What do we get? 3. It exists. Okay. Step 1 and step 2, we're covered. Okay. So then we go to the last thing. To be continuous, step 1 must equal step 2. Has to. So let's look at this. So we'll make our statement. F of 2 is equal to 3. And the limit as x approaches 2 is equal to 3. So then, since those two equal each other, which is how they state it right here, they say f of 2 and f of 2 is equal to the limit as x approaches 2 of f of x, which is actually equal to 3, which is what this is saying over here. Since this is the key one, you cannot forget all these parts. You have to state them. Then we say, yes, f of x equal to x plus 1 is continuous at x equals 2. Okay? All right. So let's just kind of slide over and look at this other one. So, oops, got to go back to this one. Control Z, go back to drawing. So let's look at this. So our f of x is equal to 1 over x. Oops, x. So then we look at this and go, okay, is it equal at 0? So if I plug in 0 right here, I get 1 over 0, which is undefined or it does not exist. We can't have a 0 in denominator. So right here, right off the bat, f of 0 does not exist. So then here's the big one again. We have to make sure we make the statement. No, list the function out, and then the big one is not continuous at x equals 0. You have to have both statements because this one here did not work. Okay, now, if you're wondering what these dots are for, 3 little dots like that mean therefore. I would rather write 3 dots than therefore. That's just a lot easier. Okay, so that's what that means. So let's walk through a few more together, guys. So here we go. We go to this one. And I've got this function here. Just think of it this way, guys. This is one part of the function it's got to satisfy. And this is another part of the function it's got to satisfy. So let's plug this in. Here's the key piece. I'm going to kind of highlight this one. Let's go to this color here. So we're looking at this bad boy here, and we know that it's got to be equal to 0, and we want continuous at 0. So now, here's the question. This is equal to 0, so we want to know when x equals 0. Now, the domain, this right here is crucial. We have to use this one because it's the only one that will allow the idea of 0 being equal to x. See how this is an equal? This is the only inequality that has an equal to it. That's why we have to use this one. Okay? So if I plug in 0 to this bottom one, so this comes from plugging in f of 0 into x plus 1, which gives us 0 plus 1. All right? Now, so that exists. Check mark. Number 1's done. It exists. Cool. So then we go here to this piece here, and we got to find the limit at 0. Now, we got a problem here. So if I look at this, let me make this a little bigger, see if it'll even go bigger here. If I look at this, and I just draw a quick graph of this, you can put it on your calculator too, guys. If I make a quick graph of this, I know at 0 to the left, it's an open dot at -1, and it goes this way. And then I know this one is a closed dot with a y-intercept of 1, and it points to the right at a slope of 1. Now, here's my question. This exists because it's got a solid dot right here. At 0, it is 1. But when I do my limit, I can't just plug it in. I can't plug in 0 because I can't plug it into both of them. Do you guys kind of see what I'm talking about? So I have to look at this graphically. Factoring and plugging it in doesn't work. So if I look at it graphically and I come in from the left and the right, so I'm going to come in from the left. So, oops, that's not the left. What am I doing? I'm going to come in from the left. That's going to approach -1. And I'm going to come in from the right. That's going to approach 1. Since they're approaching two separate values, it does not exist. Now, here's my therefore. No, it's not continuous at x equals 0. Why? Because f of 0 does not equal the limit as x approaches 0 of f of x. Okay? So then we end up with, the mouse isn't working that good, guys. So kind of look through this one. All three conditions are satisfied. Let me know in class if you guys have any questions on that one. I have a couple of little statements for you guys that we're going to look for. So let's talk about real quick about the first three continuity, or the first two continuities, and I'll show you the other ones in class. So my point continuity just means this, like there's a break in the line. All right, so it's like I got a line and there's an open circle in the middle of it. That is a point or removable. It's like an ice cream scoop came along and scooped out that. Now my jump continuity is what we just talked about. I have one here and I have an open one here. This is the graph we just talked about a minute ago. And so as I'm coming along, let's do it this way. As I'm coming along the graph, I would literally have to jump to another line. That's a jump continuity, okay? And then we'll talk about infinite discontinuity and oscillating discontinuity. They're easier to show in class because I can't draw well enough on this. So that's our notes for this, guys. Good luck, and we'll see you tomorrow.